Kids showing the road. Time to wake up. Totally new topic. We're going to talk about regression. So we're doing that section 1.3. And I want to explain a little bit of background, but for the most part, this is a section in which they usually ask you two kinds of questions. They'll actually ask you to find a regression line or use a regression line. That's going to be done on your calculator. And sometimes they might ask you about a correlation coefficient. They might describe two quantities to you with a sentence and ask you about its correlation coefficient. So let's actually talk about that. Okay. So in this section, we'll analyze called bivariate. Bivariate means we take two measurements per data point. So the idea is we want to study the relationship between two quantities, if such a relationship exists. So we measure them together. So the idea is we have two things that we want to measure and see if they might relate to each other in some way. So we can measure them. So we can say let x equals x1, x2, x3, xn be the data set. One quantity. And let y, y1, y2, y3, all the way to yn be the data set for another quantity. So for example, you might want to see, is there a connection between the heights and weights of individuals? So you go to each individual and you have one data set that collects all the heights, and you have another data set that collects their corresponding weights. So this is the height of person 1, the weight of person 1, the height of person 2, the weight of person 2, the height of person 3, the weight of person 3, and you want to see, okay, is there some sort of relationship between heights and weights, right? And what is that, right? And this is kind of when you have no clue how these things might be related. One of the first basic things you might want to do is just graph them alongside each other, plot them together, and see if there's a relationship. So this could be example weight, and this could be example heights. So then what you can do is you can go and you can start plotting them. We can create something called a scatter plot. So you pretty much go to some axes and you say, I'm going to graph the x values versus the y values. So I'm going to graph the height versus the width. And so now I want to see some sort of relationship. And you might start plotting these. So you might plot one coordinate here and say that is the x1 and that is the corresponding y1. And you'll plot a bunch of points. They'll be scattered all over. That's why it's called a scatter plot. So now your goal is to figure out, is there a relationship between these guys? So now we want to ask the question, what is the relationship here? That's what we care about. Okay? Now, one way we can study this is called looking at trends. So we collect a bunch of data, we make a bunch of measurements, we plot it on a graph, and now we want to see, does the graph give us any information about the content? So one way to explore a relationship is the use of what we call trend lines. So these are lines that best fit all data points. And their behavior will tell us perhaps we're going to talk about how it doesn't always tell us something about the relationship. So, for example, you might want to be able to draw some sort of line or curve that is the closest to all these points as we possibly can get, right? So you want the average distance between the line and all these points to be as small as possible. And so you might start to say, oh, well, maybe a curve like this seems to fit nice. That guy would be called a trend line. Because you can kind of see that, well, the dots seem to be moving up. So if I want the distance between my line and all the points to be as small as possible, the line needs to also be moving up. So you kind of somehow take a measurement. Now, to actually do this is quite complicated. You actually need some multivariable calculus to actually be able to do this properly. So we're not going to say specifically how this is done. But the idea is you can do calculations to measure the distances between points, and you want to find the minimum average distance between them so that a line is as close to all points as possible at once. Right? And such a line is called a trend line. And what that can tell us, it can tell us about the behavior of one quantity versus another. For example, if this is the trend line for this example, you can kind of see, well, as your height gets larger, your weight will get larger, right? They seem to go hand in hand together. They seem to, and the phrase would be correlate, right? In some positive way, right? People who are taller tend to be heavier. And not always. You can have things called outliers where there's just a spot that's just random out and it doesn't fit the pattern. But in general, you want to see, is there some general kind of relationship between all these points, right? And maybe then, by looking at the trend line, you'll be able to say something about these two quantities that you're interested in, right? Does this relate to that in some way that's predictable, right? Does an increase in this cause an increase in that? Maybe vice versa. Does a decrease in this cause a decrease in that? Maybe they have no relationship and it's just a mess. There are points all over the place and it seems to be no relationship. But you try to get to a relationship, right? So you can have many kinds of trend lines, and I actually did some examples here. And they all tell us something different. You can have, of course, a linear one. You can have what we call exponential. You can have I'll draw in the line that way so you can see the shapes that I'm talking about. You can have ones that are behaving like this. It's parabolic. Right, you can have many different kinds of relationships. And each relationship will tell you something different. So I think I gave you like 6 relationships here. You can have, well, let's just stop with these examples for now because I want to emphasize. So you can have, if the line, the best thing that fits it is a straight line, we call that linear. Sometimes the best thing that fits it is an exponential, right? Sometimes the best thing that fits all the points is a parabola. But you want to say some relationship about it. So here you can say, up to a point, a larger value here means a smaller value there, but after some point, now when it starts to get bigger, that one's starting, right? So you can start to see some sort of relationship and how these quantities respond to each other at different measurements. But for us, we really care about this one. We're going to talk about the linear relationship. We care about this. Okay? So that's the one we're going to focus on. Now, there are some types of linear that we would like to pursue. There's the one that's called positive correlation. Right? So this means as one quantity goes up, so does the other. You say they're positively correlated. You can have the opposite relationship. As one thing increases, the other will decrease. This is called having a negative relationship. So this is called a positive correlation. It's called a negative correlation. You can also have no discernible relationship where things are just kind of all over the place, no particular trend anywhere. Okay? So you might be able to say, okay, here we have a positive correlation in the sense that a line with positive slope is the best fit. That's why it's called positive. It's not because it's like a beat or anything. And in this case, a line with negative slope was the best fit. Right? And in the sense that a line will fit it better than any other curve. A parabola wouldn't do as good of a job. An exponential or a log wouldn't do as good of a job. A trig function wouldn't do as good of a job. The line is the best thing for candidate for the job, and a line with negative slope happens to be that. Then you have all over the place where it's like, it's kind of a wash. Just put everything down the middle. So this is called null or no correlation. Right? And it's just like a line of slope 0 is the best fit. Right? Because there's no discernible trend. You can't say one thing is moving up and the other is moving up, or when one thing is moving down, doesn't move. There's no directional information given to you here. So you can have 2 quantities that you want to study. You plot one along one axis, so one along the other axis, take some corresponding measurements, and the plots, how these points distribute themselves, can tell you something about these quantities. Okay? So we want to study this. Okay? And such a line is called, by the way, this is where the title of such straight lines are called regression lines. hence you have the phrase linear regression. So someone can say, we've performed linear regression on the data set. When they say that, what they mean is, we computed a straight line that fits the data set as best as we could. And we can talk about the relationship between the quantities by looking at the relationship between these lines. And, I have pictures of all these things. Yeah. Now, it turns out we have some formulas here. Finding the equation of the line is going to be important. Right? So we want to be able to actually find the equation so we can talk about a very specific numerical relationship. So, and again, you don't have to know where these formulas come from because it's multivariable calculus, but there's a theorem that tells us the equation of the regression line to a scatter plot of xy is given by, so we have a formula here, it's y equals ax plus b is the common notation, and your calculator will use that notation as well, where your a is actually equal to r times sy over sx, and your b is equal to y bar times a. Now, where, so that's the theorem. You can find the equation of these lines. They will have the form y equals ax plus b. Of course, a is the slope. Now the slope is computed using this formula, and I'm going to define what these pieces are. R is called the correlation coefficient. Right. Now R is the actual slope of the line. However, we multiply by this quantity to normalize it. We want to be able to draw these things. This expression is the actual slope of the line, but R is kind of a normalization factor. It turns out that our R will always be between 0 and 1. That's something that's very important. Because we want to use it on like a spectrum. R is between negative and 1 and 1. And that will always be true. That's an important thing to know. Very, very important to know. Slope can be computed by this quantity where the R value is somewhere between -1 and 1. And I'll explain what these values mean in a second. But that's called the correlation coefficient. Okay. Sy, Sx and xy are the standard deviations of x and y. Standard deviations. This is a measure of how the x values spread out. This is the standard deviation of y. So it's like a measure of how spread out things are horizontally. This is a measure of how spread out things are vertically. So if things are very pushed horizontally, you will tend to have a very small Sx. If they're spread out horizontally, you'll tend to have a very large Sx. You don't need to know the specifics of that either. X bar and Y bar is the mean average of X values. And that's the mean average of Y. Now, in a statistics class, you learn all the formulas to compute these. We don't actually care about them at this point. So that's the average x value, the average y value, standard deviations of each, and this is the correlation coefficient, which you can compute. So that's just the information. Good news is you don't need to. You don't need to know how to compute these. Not for this class anyway. In a statistics class, you'll actually do that.
So these will not be on the quiz. Would not be on the quiz?
To compute these. Nor to, technically you won't even need to memorize these formulas. It's just, I'm just stating them for your education. What you do need to know. One, you need to know about R. You need to know about R and what its value is. That's the important thing that you need to know from this section. The second thing you need to know from this section, the kind of thing you'd be tested on, you need to actually be able to find the equation of this line. Good news, on your TI 89. So you actually don't need to actually do the computation yourself. So I'm actually going to show you how to find the regression line on your calculator after we talk a little bit about R and what its values are. Because there will be questions where they're going to describe something to you and then they're going to tell you, what would you guess the R value to be, right? And they'll give you a bunch of options and you have to pick the best one, right? And then they'll ask you, okay, here's a table of values, compute the regression line, or find the correlation coefficient. Okay? So you need to know how to do these two things. Let's talk about the R value. So now, remember, and I'm going to write it down again because it's very, very important. R is between 1 and -1. On a quiz or a test or on the final, whenever they ask a question like this, they will always put a number outside that range. It is a trick. It will never be that number. The value is always between -1 and 1 inclusive. So if they said, oh, what are the options? And one choice is 1.1, it's not the answer. Don't even think about it. It's a trick. It is always between -1 and 1. Say it all the time, students still pick numbers outside that range. It will never be larger than 1, it will never be smaller than -1. Under no circumstances. It is a trick. Okay. Right, so that's the first important thing you need to know about R.
You said that'll be a question on the final?
Yeah, there's, on the test, on every test. There'll be a question like this where they're going to describe a situation and they'll ask you, what do you think the R value would be here? You'll be given a bunch of options, right? So they'll be like, is it 0.2? Do you think it's 0.9? Or do you think it's -0.7? Or is it 1.4? That 1.4 is a trick. It's automatically eliminated. You don't even think about it. It's always between here. Okay, that's the first thing. Now here's what they mean. And it's about, really what it is, it's about the positive and negative and zero correlation. So here is the rules of R. Okay, so it's kind of like on a spectrum. I don't know if I should put this other bullet one. So here is the situation. R is close to 1. Okay? Now, again, if you're judging something by eye, you won't know the exact value. You have to actually do some calculations. But you can know it's close to 1. Like, is it 0.99 or 0.9 or 0.89 or something like that. So you can have a certain behavior when R is close to 1. You can have another one when R is close to -1. And there's another situation where you know R is close to 0. Okay? So So you can make judgments based on these three guys. So you can think of the R value that runs on a spectrum between these three basic situations. Now R is close to 1 means the following. The points fit very close to a line of positive slope. So the closer it gets to 1, the tighter the fit is, right? So you can have something like this, like the points are super close together, they're super close, they're very tight fitting towards a line that has a positive slope. Okay? Now the more spread out the points start to become, the farther away from 1 you will go. Okay? So that's important. Now, close to -1 means a very strong negative correlation. So you can think of this as a very strong positive correlation. R is close to -1 whenever you have a very strong negative correlation. So this means the points are not spread out very much, they're very close together, but they happen to be close together to a line with negative slope. So if you see a situation like this, it means it's very close to -1. And the more spread out you become, the farther away you go from -1. Have what we call a very strong negative correlation. R is close to 0 is kind of the null situation. The best fit is a line with 0 slope. Things are so spread out you can't say there's a trend up or down. It's just all over the place, very scattered. At that point, a horizontal line is the best you can do to measure where everyone is. And so this means the points are very scattered. A line of 0 slope best. Now I do want to mention here, even though it's not really important for us, is that actually achieving 1 or -1 is near impossible. Like, to be -1, for the R value to literally be equal to -1, you have to literally be on the line for every single point, which is it's not going to happen, right? So you'll always get close to 1, like 0.99 or 0.9 something, right? And that's sort of the best you can hope for in reality. There's always going to be some deviation, some guy that's just out here or whatever, but a perfect 1 means everyone is literally on the line. And a perfect -1 would mean everyone is literally on the line. But you get close to these values, when they're very close to the line, there's some little bit of spreading out, but not much. So if I were to say something like, guess R, and I did the line, and I said, here are the options. Is it minus 0.7 B? Is it 0.99 C? Is it minus look at that picture. Let's say this random picture was thrown on an exam or quiz, and we were saying, what do you think is the best value for R in this scenario? Huh? What? You guys?
No. B.
Okay.
B.
So you should immediately recognize, hopefully,
It's B.
that that is gone, right? C is also gone, right? If you choose one of those, you have no idea what you're talking about, and it's really bad, right? It will always be within this group. Those were tricks. They're meant to kind of scare you away.
The two negatives are gone.
The negatives should be gone as well, because remember what it means for the R value to be negative. It means you're sloping downwards. Clearly here the line is moving upwards, so it's definitely one of the positive numbers. So now of these two, what would you say?
D.
D. Because 0.99 is super, super close to 1, right? You'll have to be a lot tighter, right? Now, of course, it's kind of a qualitative kind of guessing game, but you can see, you would expect a 0.99, right? Like a 0.99 should be like, they're like here, right? Because 0.99 is super close to 1. You shouldn't have a lot of spreading out. But with this, you see some spreading out. You can see a very clear upward trend. So 0.8, 0.7 seems about fair, right? So you will be asked to eyeball some things, or you will be asked to, they'll describe some situation to you, and you have to say, I would guess that the R value is this. Sometimes they might even say in something in words. They might say something like, oh, did I have some examples? There's some really funny examples. There's the notion that correlation does not imply causation. Have you guys ever heard that phrase? Have you ever heard that phrase? So it turns out that this is not like a perfect science. Like sometimes the relationship that you develop isn't the best, and it's actually not true. So, for example, it turns out that the rate of violent crime has a very strong positive correlation to ice cream sales. The more ice cream people buy, the more people become victims of violent crimes. So every time you have a bad day and you reach for the Haagen-Dazs and you're there, you should know you're contributing to violence, right? You monster. Put the tub of ice cream down. The more ice cream people buy, the more people actually die from violent crimes. That's actually true. Like if you were to plot violent crimes on one axis, ice cream sales on the other axis, the points will fit very closely to a positive line. Now, is ice cream directly responsible? Well, no, but there are suggestions. And so sometimes they might describe a situation to you and they might say, oh, we noticed that, you know, the more lemons that we sell, you know, the more traffic fatalities happen on highways. What would you guess the R value to be, right? So they'll say something like that. And you have to say, okay, it should be positive based on what you described, or something like that. So they might describe in a sentence, and you just have to look at the relationship. So essentially, R positive means if one increases, so does the other. So that's another way you can look at it in terms of a sentence perspective. R is negative means if one increases, the other decreases, right? So if they have the opposite movement, right? One goes up, the other one goes down. You say there's a negative correlation. If both go up at the same time or both go down at the same time, there's going to be a positive correlation. At this point, I am going to tell you, and again, you guys should definitely be reading through these handouts. Sometimes I just go over the highlights. So at this point, I'm actually going to tell you how to compute the R, and you'll need a calculator. So I gave an example. Here are some X values and Y values, and this is pretty typical. Like on a test, you'll be given 3 or 4 values for each usually. So it's like, here's one, when X is 1, your Y is 1. When X is 3, your Y is 12. And when X is 5, your Y is 10. So they might ask you to do that, and they might say, based on the scatter plot, would you say R is positive or negative or something like that? And sometimes they'll actually give you a list of values and you have to choose between them. So you could actually draw a little graph here. We're mostly going to do this on the calculator, but so when X is 1, your Y is 1, so that's 1 point. When your X is 3, Y is 12, another point. When your X is 5, Y is 10, that's another point. So what would you guess? So a line that's pretty, so you to get a line close to these two, it has to be going maybe in between them somewhere around here, but then to get it close to that, it should be going down like that. So that might be a line, and you might say, I would guess it's slightly positive. So things like that you should be able to do. Now, what's more important is that they might give you this table. So now here's the important question. So usually there's always going to be an easy question with regression where they're just going to describe a situation or give you a plot and ask you, is it positive or negative? Or what value would you guess it is? And based on how close it is to a line, you would guess, hopefully guess correctly. But the more technical question is, and this always comes in the calculator section because you need your TI-89 for this, so you can start working those out, is to find the equation of the regression line. And, or sometimes they ask you to actually do both. Find R, the correlation coefficient. Actually find its specific value for that data set. Let us actually do that. So this example, it's in the sheet. So and also the steps actually do this are here. Forewarning, as far as working on your calculator goes, this will be the most complicated thing you do this semester. And it is something it's definitely coming. I'm definitely going to put it on a quiz. It's definitely going to be on the first test. It will definitely be on the final. So just take the time to learn this. Right? Every semester I have a student, I don't remember, what was I supposed to do again? No, don't end up in that position. Learn this. This is super important. Okay? So the steps are all here, and it's kind of, you're going in different places in the calculator, so you really need to know where you should be going at any given time. Right? So the instructions are here. We're going to follow them with this particular example. And like I said, you can expect 3 to 4 points on an actual test or the final. So they'll give this table to you, and then they'll say, find the equation of the regression line. The final is usually like multiple choice. So you'll have a bunch of things with a bunch of decimal points. Is it y equals 0.078x minus 3.19, right? Or is it, they'll give you a bunch of lines, so you have to pick the right one. Okay. So let me show you how you would actually do that. Make sure you write this down, and we're going to actually I always have to go down and up to go. I don't understand. Hit the lights here. Except the moon. Okay, so now we're gonna have a regression line. I have those points here. Okay, so the x value is 1, 3, and 5, and the corresponding y values is 1, 12, and 10. So you guys have that written down in your notes, hopefully. So now let's actually go through this process. First step, turn the calculator on. I should have put that there. So let's make sure you're at your home screen. So that's the home screen. Okay, so the first thing you want to do is you want to check that your calculator is in the right mode. Usually if you set it, it's not going to move, but I would always double check. So you would go to mode, and you need to make sure that that thing that's blinking is saying functions. Okay, and if it's not saying functions, you need to change it. Okay, so it says there's an arrow here, so you can press this arrow, it'll drop down a list, and if it's not set to function, you need to set it to function. That's the first important. So that's not actually to do something, it's just that if that's not set to function, something's going to go wrong. Okay, so once it's set to function, it usually stays there, but just make sure it's there now. Okay, step 2, you're going to go to apps, applications. Okay. Now what we want is the data matrix editor. Okay, that's where we're going to put in the table of values. So we're going to move down, data matrix editor. And you're going to start a new one. Okay. Now, you're going to give this a name. So you're going to scroll down here, and I don't know what we'll call it. Call it something random, XXX. It's just a name. So you're just saving it so that you can save a list of these data sets in the calculator. So you're just saving it a name that you can recall later if you need to recall it. Okay. Enter. Okay. So once you do that, you press enter twice, and that will bring you to the table. Right? Now, as you can see, the calculator can accept more than 2 corresponding values, but we're just going to enter 2. Namely, we're going to enter them in C1 and C2. I like entering the X in the C1 column and the Y's in the C2 column. So let's actually do that. So this is 1, enter, 3, enter, and 5, enter. Okay, you can use these arrow buttons to move somewhere else in the table if you want. So go back up, and the corresponding Y was 1, enter, 12, enter, 10, enter. Okay, so you enter those guys. Okay. Now, you're going to start to calculate the regression line. This actually brings us to the F5 function. F5. Right? So F5 says to calculate. It can plot, again, it can plot many different kinds of trend lines and stuff like that, so you kind of have to tell it where you want to do. So we're first going to go to type, and we're going to tell it that we want a linear regression. Okay? So you go sidebar and then here. Now be very careful, 5 and 6 look very similar, but they're very different, and I don't know why they put them together, but see, it's always good to see something. You want the LIN, that stands for linear regression. LN is not linear regression, it's actually a log regression. Okay, so you want 5 LIN reg, linear regression. So you're gonna set that. Okay. Now you're going to go down and you're going to tell it where do you want to take your X and Y values from. So you might remember in the previous table we set the X1 from the C1 column and the Y from the C2 column, so that's what I'm going to enter here. And you use the alpha keys to help you here as well. So C1 goes down. Is that actually alpha C1 down, alpha C2 down. Now, you can tell it where you want to store the equation to. Just in case you need to pull it up quickly, so you can save it into any one of the functions in your Y window. So you can save it to Y1, Y2, Y3. Let's save it to Y1. Okay. So, once you enter the data in the table, you're going to press F5 calculate. You're going to enter linear regression. You're going to put C1 and C2, and you're going to save it somewhere. Okay. And now you're done. So that is actually the calculations here. So let's actually write that down. So here it tells you y equals ax plus b. The a is 2.25. The b is 0.916667. So usually they'll put an answer on your paper. Just round to whatever decimal places that you want. So in our case, this was, let me write this down. So your A is 2.25, your B is 0.9166. Let's just put 0.9167. Now, CORR, that's your R value, so that's the correlation coefficient. This one is actually a 0.76. So this is, the R value is 0.76. Looks like 0.7680 or 4 decimal places. Now, there are some contexts in which people like to use the R squared value. They like to keep it positive. We don't worry about that. So sometimes they'll tell you an R squared value instead of the R value. That's when they don't care if it's positive or negative. They just want to know how close it fits. So the correlation, that's the R value. So if the question asks you to find the R value, in this case it's going to be that. That's the 0.76. So once you have that, it's okay. So that was, and so now these would be the values. So the equation of this regression line, the line that goes through these 3 points, is going to be y equals 2.25x plus 0.9167. That would be the equation of the line that does that. And that pretty much is it. Now this last part here, we're going to do it just because it's cool. You'll never be asked to do this, but I think I wanted to show you guys anyway. So this is optional. So step 8, that would be it. So a question would ask you, okay, here's the table. They'll give you this table. Compute the regression line, right, which you'll usually pick from a list of choices. Or they might say, find the R value for this thing. And they'll give you a list of choices. And you go through that whole process I just got, and you'll end up with that data here. Okay. Now, I want to show you guys how you'd actually graph this and graph the regression. So that's the optional step. So let's see how we want to do this. So, let's run through this because I think I lost my place. Okay, so to run through quickly again, is new, go down, call this something random, enter the data, 1, 3, 5, move to the side, 1, 12, 10, calculate, regression, down, C1, go down, alpha, C2, down, let's see this guy in 1, there's the data. And I believe from there you can press OK to. Sorry, you're supposed to go to F5 first. 5, and you press that. Press F2, display the plot setup screen, plot, highlight plot. So highlight plot 1. With plot 1 highlighted, press F1 to define plot 1. Now we're going to set the plot type to scatter. It's already entered. And we're going to tell it where we want the data again, so C1 and C2. Enter, go to the Y editor, and so now you can kind of see that that weird thing right there, that's actually the regression line that we computed earlier. So now we want to go to style, so we want to tell it that we want to plot, so style is F6. Tell it we want a dot plot, not a line, so it's not going to connect the dots here. Get F2, and we're going to scroll down to zoom data. Check it out. Oh, there's the old guys. Let's get these guys out. Come on, come on, come on. Let's erase these old guys. Dot. So there, it plotted the points for you. That's 1, 1, 3, 12, and 5, 10. And then it actually drew the line that best fits them. You can see it's a line of positive slope. In fact, we know specifically what the slope is. It's actually 2.25. I think that's just cool. You'll never be asked to do this, but I think it's just good to show you that you can be done. So that's just like step 8 here, which is optional. So that pretty much ends what we need from this section. So basically you know how to do that on the calculator to find this. And you can understand. And so here, the regression line equation would actually be the equation y equals 2.25x plus 0.967. And the r value will be 0.76.
Would this be on the next?
B is the y-intercept of the line.
No, I'm saying would this be on the next quiz?
Oh yeah, yeah. So next week I'm going to actually ask you how to do this. Find the regression line for something. And tell me about an R value. But that's pretty much it for 1.3. You need to know those two things. You need to be able to talk about the R value and be able to find this data. So one is in a calculator, it always shows up on the calculator section, and the other question usually shows up in the non-calculator section. Right now, We're actually going to go back and review some stuff.
Oh, no.
I want to remind you about functions. We're going to need to know about them for the things we're about to do in calculus. The calculus starts in chapter 2, but I want to
We're
review.
still not on.
Yeah.
We have nothing.
Calculus starts in chapter 2, but we are going to need to review some algebraic ideas before we get there. Regression is kind of a standalone thing. It's more of a statistical thing, but now we're getting on back on track to calculus. We're going to talk about functions. So let's talk about definition. What is a function? A function is a rule it's actually one in set code. So here we're defining function, what its domain and codomain are, and what its range is. So function is just a rule that assigns to every member in one set. This original set is called the domain. It assigns each member there exactly one member in another set called the codomain. The people who get some assignment in the codomain are called the range of the function. So you can pictorially, you can see here there's one thing called a domain. There's another thing here called the codomain. So what a function does, it has a bunch of people over here, and what it does, it will connect each of those people to exactly one person over there. Now each person here can connect to the same person over there, that is possible, but it's important that there's only one line leaving each individual here and connecting to something over there, right? Now, the people who have been chosen for an assignment, they are said to be in another set that we call the range. So these two people are in what we call the range of the function. And these two people are not in the range of the function. So here I can name the function, say f. F is going to be a rule that takes this guy, connects him to that guy, this guy connects to that guy, this guy also connects to that guy. So that's basically it. So a function is a way to define a specific kind of relationship. Usually for us, of course, it's math class. It's going to be numbers, and we're going to have a formula that connects it to other numbers. But this rule actually applies in general. You can think of many things as functions. And you can also think of many things that are not functions. So here's an example of a function. Another example of a function would be something like this. Here, each person goes to one other person, and that person is distinct from any other person that was chosen before. So this is what we call a one-to-one function. This is what's called a many-to-one. But they're both functions. They follow this rule. You can have a situation that is not a function, situation that does this, for example, is not a function. You can have one person connecting two things. That's not a function. It's also not a function to have something like this happening. These are not functions. So this one is not a function because here you have one thing in the domain being connected to two things in the codomain, where the definition requires exactly one connection must be made. Here, this is not a function because you have someone in the domain to which no assignment must be made, and you need each member to have an assignment. So literally everyone in here must have an assignment to someone over there, and they can only have one assignment to someone over there. That is called a function. Okay? So for example, if you're taught, and again, you can think of this in general terms. So for example, being a father of someone, biological father, is a function, right? I don't know where science is going to be in a few years, but each person only has one biological father. Now you can have a father with two children, but from this direction it is a function. If you look at the idea, for example, having a Facebook friend is not a function, because one individual can have many Facebook friends, right? So if I want to study parentage, setting up a function might be something that I can do to study that in detail, whereas if I want to study having Facebook friends, setting up a function is not something I would do, because it doesn't fit the definition.
So two domains can go into one codomain, but one domain can go into two codomains?
Everyone here must be connected to one person there. Now they could be connected to all the same person, that's fine, but everyone on the domain side must have one connection. There must only be one line connecting. This is not a function because you have two lines. So that's the idea of a function. It describes a special relationship in which everyone in one group is connected to only one thing in another group. Or set, I should use the word set because group means something else.
But isn't that connected to one?
What is?
First function.
This?
Two connected to
If I call this A, B, C, how many people is A connected to?
one.
How many people is B connected to? How many people is C connected to? That's a function. Each person is connected to one thing.
This means the x value cannot be double and only the y value.
Yeah, if you want to talk about graphically, a function would have to pass what we call the vertical line test. So we're kind of jumping the gun here, but we can talk about it now. Graphically, functions pass what we call the vertical line test. So for example, y equals x squared is a function. If x's are here and my outputs are here, because any vertical line will touch this function at most one time. It means every x value will only be connected to one y value and no more. Right? So any vertical line will only touch any vertical line touches the function at most once. Right? It might not touch the function at all, but if it does, it needs to touch it one time. Non-functions, things that are not functions do not pass the vertical line test. For example, a circle is not a function. Right, so the equation of a circle is x squared plus y squared equals 1, let's say. And you can draw a vertical line that touches the function twice. Meaning this single x value has it's connected to two y values. Right? So that makes it's not a function. So we're going to look at graphs and ways to represent functions presently. Okay, let's see what I wanted to define. Function, domain, codomain, yes, define that. Range, I defined that. Let's talk about inputs and outputs. We can name functions. Usually, not always, with lowercase letters. So we can call a function f, for example. I'm going to say that's its name. This is the function f. Let one be f. Then there's the idea of the variables. Definition. The term input, this is a domain element. We might call it an input. And outputs are corresponding range elements. Use input and output to talk about those two things. Now, we can also define variables. We can talk about an independent variable. This is just a variable that represents an arbitrary generic input. So if you want to say something about all the input elements, but you don't want to say it about all of them at the same time, you just want to say, if you take any input element, this will be true, you can use an independent variable to describe that. A dependent variable does the same for the output elements. This describes arbitrary / generic range elements. And we can talk about so the idea here is the following. Here's x, it represents some arbitrary input that I can put into a function. Now a function is just a rule, which is called f. It's going to be a rule that does something to x or connects it to something. And then the function, after doing that calculation, is going to spit out another variable, which we call y. And these just talks about generic variables here. And so, for example, you can say, okay, if this guy is x plus 1, for example, so you'd realize that if you put 1 into this function, it's going to spit out 2. And if you put 3 into this function, it's going to spit out 4. If you put minus 7 into this function, it's going to spit out minus 6, right? It'll do some calculation. It's going to say, whatever you put in, add 1 to it, and that's going to be the output. And x represents any arbitrary such guy. This is just something that represents. Anyone you want to pick from the domain, consider that guy x, and throw him in this function, and it's going to do something, and that's going to be the corresponding type of the range that's going to come out. And the y's would represent those guys. So the variables are kind of like your category or demographics or something like that. Whereas you can have the individual values like your name. You can just talk about all students in this class. X represents some student in this class. They're very individual students in this class, but they can connect to other guys. Okay. So now I can talk about some notation here. If we say f is the function, x is the independent variable, y is the dependent variable, we can write the following. You can say y is equal to f of x. So this is red f of x, where x you consider as the input, f is the name of your function, and y is the corresponding output. So you really want to kind of have this picture in your head. This is just a rule. X is put inside of that rule. And this is just a rule that's computing what the output value is, and y is going to be the corresponding output value. And to name a function or describe a function, or to both name a function and state your variables who you're choosing to be the independent and dependent, you can write down a phrase like this, and it would mean just that. So I can say, I have a function f, a generic input I'm calling x, and a generic output I'm calling y. And this equation conveys those ideas. What do I want to, okay, sorry, define all those. Another notation. Say the domain set is called A, and the codomain set is called B. Then we can write F colon A to B to mean there is a function f from A to B that is f takes elements of A and assigns them to elements in B. So for example, I might say something like f goes from the real numbers to the real numbers. So you plug in a number on the number line, and it will give you, as a result, a number on the number line. I can also talk about f is a function from the real numbers to the English alphabet. Right? So I could define a function like, okay, this is a function that gives you the first letter of the name of the number. So if you plug in the number 1, it will output the letter O, right? If you plug in the number 2, it'll output the letter T, right? There's always some rule that no matter what you plug in, there's only one thing that it could possibly connect to that could somehow be determined by the rule given. Okay, so that is a function. ways to represent functions. Many ways to represent functions. One, mapping diagram. Those are like the pictures that I drew earlier. So this is like you draw the bubbles for the domain and codomain, and you draw connections. So let's say 1 goes to 3, 2 goes to 5, goes to 10, etc. What is the rule here? So assuming f goes from real numbers to real numbers, this is describing f, where f goes from, say, real numbers to real numbers. I wrote down a few examples for you to get some clues. What would you say f is here? Do you see the rule? That one, I want to choose 7. Now do you see the rule?
Times 2 plus 1.
Times 2 plus 1. Yeah, that was the bad guy, right? So this says multiply by 2, add 1. Right? So that's the rule. I can express that by literally drawing this picture. Sometimes a function you don't really know how to do with it. You just draw pictures, start making connections until something becomes evident for you to be able to figure out the rule. Another way to figure out a function is a table of values. So in the same way, I could say x and y, and I could say, okay, 1 would go to 3, and 2 would go to 5, 3 would go to 7, minus 1 would go to minus 1, 4 would go to 9, etc. It's called a table of values. You can see a function that way. 3, you can talk about a set of coordinates. Is another way you can see functions expressed often. So you might see f is equal to a set of coordinates. So you'd say like 1 would go to 3, 2 would go to 5, minus 1 goes to minus 1. And here you put the input, and here is the corresponding output. And you should notice for a function that all possible input values must appear, and they must appear once in the above list. Otherwise, it's not a function. So you can put the input in the first position and the output in the second position. Another way to represent a function, we call it algebraically, or by what we call a formula. So then we can use the notation that I introduced here. So we can say f of x is multiply by 2 and add 1. And this expression would describe mathematically what we're doing with x to get the y. So this is how we would compute corresponding y values for some given input value. Double it and then add 1. And that is the rule. So we can express a function that way. Another way to express a function, graphs. So that's when you draw a picture of the function. Thanks to Descartes, we have the xy plane. So you can put the inputs on the horizontal. So whatever you're thinking of as the dependent variable, the independent variable, and here you put the outputs on the vertical. That's where you have the dependent variable. So usually in most cases what that means is the guy that's on the horizontal is the guy that you don't control, and then the guy that's on the vertical is the guy that's responding to that guy. So oftentimes if you're plotting things like depreciation, you put time on the horizontal. Time is not something you can control. Time is just doing what it does. It's independent of you. But then you're looking at the value of your quantity and see how is it responding over time. Okay? So that's why we tend to call this the independent variable. It is what it is. The dependent variable depends on what that guy does. And so for a given input, this guy's output will respond in kind. So many ways to represent a function. Verbally, the dreaded word problem is the last way. Verbally. Example, word problems can describe functions to you. So even like on the quiz where I said, okay, to rent a car, it's a $20 flat fee plus this many times miles driven. That sentence you could translate directly to an equation. It's a way of describing how to compute. The output being the cost to rent the car, the input being the number of miles you're driving. Okay. So this is just describing a function in words. So in this case, you would just say, you literally write down the phrase, multiply by 2, add 1. Let's talk about evaluating functions and then we'll wrap up. So we can do something called evaluating a function. This is computing an output for a corresponding input. Especially if as a formula. So, for example, if f of x equals x squared plus 1, I can say what is f of 2, and this is basically me asking you to evaluate f at x equals 2. How you do that is you simply follow the rule and you replace the 2 with the x plus 1. Now it's important, your view of functions, and I'll definitely talk about this next time because we'll see it become an issue soon. To notice that whatever happened in parentheses here, what happens to that is I replace the x value with it. Whatever was here is now put here. Right? So one way to think of function formulas independent variable, whatever it is, could be an x, could be something else. Are placeholders. Okay? So For example, if you see f of x equals, say, x squared plus 3x minus 1, you should think of it this way. And that will save you a lot of trouble. Think of it as the x is a placeholder. This is blah, it doesn't even have to have meaning to you, right? You want to think of the function as the x is just, there's a gap there. The x is just telling you what to put in this guy goes in computing the formula. So whatever you put inside here, you have to put there and you have to put here. So I can talk about what is f of 2 in this case, and I would think of that as, we'll just put a 2 here and a 2 here. Let's see. Let's use another color. So if someone puts a 2 here, you know I put a 2 in this position, I put a 2 in this position. And if someone asks you, what is f of something else, like what if they ask you, what is f of x plus h? You should know I put an x plus h here, and I put an x plus h here. It's a very common mistake for people to just copy down the formula and then put a plus h at the end, because you're not thinking of the formula correctly. The x's are placeholders. Whatever goes in the parentheses here, you replace every single x with it, you open up parentheses, and you just drop it in, right? So if someone asks you, doesn't matter, they can ask you, what is f of a squared? What you're going to do is you're going to put a squared here, put a squared there. Someone can ask you, what is f of smiley face? Put smiley face here, put smiley face there. Do not complicate it. No matter what goes here, put it where the x's were in the original formula, right? You don't want to think of this as like an immutable thing that if I ask you f of x plus h, what you have to do is just add an h here, because that's wrong, right? The x's are placeholders. Whatever goes here, and it goes here. Right? Whatever goes here, goes here. Right? That's how you want to think of it. The x is just a position. Remember from the definition, your x just represents an arbitrary generic input element. It's not stuck there. It's there as a placeholder to represent someone else being there. Right? It's someone standing in your spot in line. Once the person shows up, they take that spot. Okay, so we'll stop there. And we'll pick up with that next week. So next week's quizzes will be, of course, everything we did today up to this point. And of course, I do expect you to know, if you had x plus h all squared, how to deal with that. What is that?
X squared.
X squared plus 2xh plus h squared, etc. You have to like expand and do all that stuff with it. We're going back over stuff, but we're not going back over everything. I also have quizzes to get back from last week, so.
Are we like behind?
Huh?
Are we technically like behind?